For a long time, we have not discussed science or topics related to science. So I thought let us discuss diffraction from a higher secondary point of view so that most of you can understand it. Less mathematics, more philosophy and physics. To understand dif- diffraction, we'll use a simple single slit. When we shine light through this slit, we do not get a simple sharp projection of light. Instead, we get intricate pattern, a wide, intensely bright central band, followed by a series of dimmer, alternating bright and dark fringes. This phenomenon is known as diffraction. This challenges our simple ray-based intuition about how light travels. In this presentation, we will see why this happens. Now, let us first think how we observe diffraction pattern. So what we need is a monochromatic source of light, then a lens L1 which is collimating the light beam coming from the source that makes it a plane wave. So it generates plane wave fronts that is incident onto a slit, single slit. Slit width is B. When it passes through the slit, in front of it, we place another lens, which is a focusing lens. So the light coming out of the slit gets focused by the second lens, lens 2. At a distance d from the slit, there is a screen, and the second lens focuses the outcome light onto the screen. Now, intuitively, let us see a classroom door or a garage door. If the door is widely open and many students are coming or many people are coming, now wide open is the slit width, opening is width B. So if it is wide, then if the crowd is trying to exit through that door, when it is wide, everyone will walk straight through it without any problem. But if it is narrow, then the crowd or the students and they will fan out to fill the space on the other side of the door or the that is the slit. This is equivalent to diffraction in light. The wave is forced to bend and spread out. Here that we can see from this. This fanning out is the key. But why does it create a pattern of light and dark fringes in case of light? Let us discuss that. So the key lies in something called Huygens principle. When a plane wavefront encounters an aperture, every point on the wavefront within that aperture acts as a secondary source of wavelength. So every point is another new source. So the light in the single slit is not coming out of a single source, but it is an infinite number of coherent point sources distributed continuously across the width of this slit. The diffraction pattern is the resultant of all these tiny wavelets which interact with each other. So in the slit, there are many sources, infinitesimal sources. Each source is sending light, and those light from each source they interfere with each other, forming a particular pattern which we call the diffraction pattern. Earlier, you must have heard the term interference if you are a science student, either in the higher secondary level or in the graduate level. In interference, we use two slits. Instead of one slit, we use two slits. Each slit is considered to be a source of light, and the light coming out of that slit interferes or superposes on the light coming out from the other slit. On the other hand, in diffraction, we have single slit as we have discussed. The superposition is from infinite continuous coherent sources. The critical difference here is a single slit interferes with itself, whereas in interference there are two slits, so the interference is between two separate sources. Now let us try to understand the geometry of interference, particularly what is the path difference. Consider one slit. So the slit is from A to B. Slit length is B small b. Now the light ray is passing through this slit and in the same direction from point A, the direction in which the light ray is going. From the point B, it is the same direction in which the light is going. Therefore, if we consider a point P on the screen, then the light rays are incident on that at an angle theta. Now you can ask how that can happen. One point on the screen, 2 points on the slit, how these two angles will be same. Remember that from geometry, we know if we have two parallel rays, they meet at infinity. The screen is at such a large distance that this distance is practically infinite, at an infinite distance with respect to the extension of the slit. That is why it is theta. And the for both the rays, from the ray from A and for the ray from B, it is theta because of that. Now from A it travels certain distance, from B it travels certain distance. These two distances should not be equal. There will be some small difference between these two distances. This difference is called the path difference. How to find the path difference? From point A, drop a perpendicular onto the ray traveling from point B. Where the perpendicular meets the ray from point B, the distance from point B to that meeting point is called path difference. Let us call it delta x because the ray is traveling in x direction. So delta x will be, look at the geometry, delta x will be then b into sine theta. B is the hypotenuse of the right angle triangle. From A we have dropped a perpendicular, so it will be b into sine theta. Theta is the angle between the hypotenuse and the perpendicular dropped from point A. So this is the path difference, and it is the root cause of the entire pattern, whether it is in interference or whether it is in diffraction. Now, when these rays coming out of A and B or from the slit, they meet at a point, they form a pattern of bright and dark light regions. Why these bright and dark light regions are formed? That is the question. So consider the angle theta, where the path difference between the top and bottom of the slit is one full wavelength, which means b sine theta is equal to lambda, lambda being the wavelength of the light. Now at this angle, the wavelength from the top edge is perfectly cancelled by a wavelength from the center of the slit, because up to the center it will be the wavelength, this path difference will be lambda by 2. Now when it is lambda by 2, why it will cancel out? Now you can see that from the picture. In the picture, there are two sine waves. On the rightmost side of the picture, there are two sine waves. Now in these sine waves, for the top one, the peak is at the crest of the bottom. Similarly, for the crest of the bottom one. So they are exactly 180 degree out of phase. So plus one is suppose top one is suppose plus A, then bottom one will be minus A amplitude. So plus A plus minus A is equal to 0. So that creates destructive interference, or we get interference which gives a destructive superposition of two waves. So that waves cancel each other, giving us a dark region. So darkness is coming from this. Next. Now, how you get bright center? When all the wavelets are adding up. So the top one to bottom one, everything from every point, find out those points from which if the ray is going, then the peak of the wave for every point from the slot or the slit, they are in phase. So peak is the top ray peak is on the second ray peak, the third ray peak, all are perfectly aligned. So they will add up, giving a constructive interference, so giving us brightness. Now in this case, sine theta is equal to 0. If theta is equal to 0, so there is no displacement between the peaks. Theta is equal to pi by 2 means there is half wavelength displacement between the peaks, or 180 degree displacement between the peak, because of which we get destructive interference. Here it is 0, so we get constructive interference. So path reference delta x for all wavelets is 0 here. Every single one of the infinite wavelet arrives at the center of the screen perfectly in phase. So they interfere constructively, adding together to produce the intensely bright central maxima in case of diffraction. This is where the intensity is at its absolute peak, I0. I0 intensity, we know, we define it as the I0 is the square of the amplitude of the wave. Next. Now this we have already discussed. We consider a single slit as a chorus of infinite wavelets. So how does one opening create a complex pattern of light and dark? The key is to treat the slit not as a single source, but as being filled with an infinite number of point sources, each emitting its own wavelet, or based on Huygens principle. The pattern we see on the screen here is the result of those countless wavelets which are interfering with each other. Next. Now let us define the geometric framework for this and explain how this happens based on geometry or based on philosophy. To analyze the interference, we need a consistent geometry. We define the slit width as B and consider the light traveling to a point on a distance screen at an angle theta. So slit width B means here the difference between the two single slits. That difference is B. Okay. The crucial quantity is the path difference between the light from the very top and the very bottom of the slits. So that gives us the path difference delta x, which is path difference, is B sine theta, and that is being projected at a distance screen. Next. Now, how you get the central maximum that we have discussed? It is unity and amplification at theta is equal to 0. At the exact center of the screen, the angle theta is equal to 0. Remember, what we are seeing here is magnified view. So theta is very small, approximately equal to 0, so we can take it as 0. So therefore, the path difference between all rays is B sine 0. B sine theta is B sine 0, which is 0. Since path difference is 0, as we saw from interference, there will be constructive interference because the path reference is 0. So if there is constructive interference, every wavelet from the slit travels the same distance. They arrive perfectly in phase and interfere constructively. That results in maximum brightness at the center of the screen. Next. Now, how we get the first minima? After that bright spot at the center, how you get the minimum? The logic for perfect cancellation. What is the logic? The first dark fringe or the minimum that will occur when light from the slit perfectly cancels itself out. Now, how do that occurs? Now, let us propose the condition for this to happen. What is the condition? Condition, as we have discussed, is total path difference across the slit is exactly one full wavelength or lambda. So that phase difference is pi by 2 or 180 degree. Next. Now, let us see the proof, philosophical proof of that. Let us start with two-zone model. Suppose B sin theta is equal to lambda. Somehow we have got B sin theta is equal to lambda. B is the slit width. Now we can logically divide the slit into two equal halves. The upper half, the blue half, A zone, and the lower half, the orange half, the B zone. For every wavelet source in the top half in the A zone, there is a corresponding source in the bottom zone for which the distance is of b by 2 away. So A to B distance is b by 2. Okay, so for every point on A, upper half, blue half, there is a point on B which is at a b by 2 distance. Why? Because we have divided it at the center. So center is b by 2, total slit length is b, center is b by 2. If you are at the topmost point of the blue half, then the bottommost point of the blue half, or which coincides with the topmost point of the orange half, is at a distance b by 2. Then you come from there down below up to the orange top, and gradually everywhere you will get a point in the orange half at a distance b by 2. Okay. So and there is a point b by 2 always. The path difference between these two specific pairs is b by 2 sin theta, that is lambda by 2. So phase difference is pi by 2 or 180 degree. Now a path difference of lambda by 2, it causes a perfect destructive interference because every point on the top half has a cancelling pattern in the bottom half. The entire slit's contribution is nullified. So every point on the top half is getting cancelled by a corresponding point on the bottom half. So everything is on the top half, everything is getting cancelled by from the bottom half. So complete destructive interference, combination of destructive interference giving us a yeah, non-bright or dark zone. Next. Now let us generalize this minima for multi-zone model. So what we'll do, we'll consider a case for n is equal to 2. So two blue zones, two red zones. In the upper half, for every point on the blue zone, there is a point on the red zone for which b sin theta is equal to 2 lambda. Same thing happens for the bottom half. So for the upper half, there will be phase cancellation. For the bottom half, also there will be phase cancellation. A minimum will occur whenever the slit can be divided into an even number of zones that cancel out in pairs because b sin theta is equal. So that will happen in case of b sin theta is equal to n lambda, n has to be even number. Sorry, n has to be 1, 2, 3, 4, etc. But n cannot be 0. We'll see why n cannot be 0 later. But n at n is equal to 0, remember that it will be the central point, which is the maximum. So n is equal to 0 means b sin theta is equal to 0. Therefore, that will give us the maximum. Next. Now, where will be the secondary maxima? So, first central maxima, then there is a dark zone, then there is another maxima. So, logically, what will happen? What happens if the bright areas between the dark rings? These are the secondary maxima, we call them. Logically, they will occur when cancellation is incomplete. There is no complete cancellation. So there is some amount of cancellation, but not complete cancellation. So since cancellation is incomplete, there will be some amount of brightness. So these are called secondary maxima. Now let us take the condition halfway between the center and the first minimum. So if we consider the center and first minimum, a total path difference of 3 half wavelengths will be there, which means b sin theta is equal to 3 lambda by 2. We will consider this range. Okay, next. Now, if that occurs, what we will do is we will divide the slit into 3 zones. So, if we divide the slit into 3 zones, 3 equal parts, the wavelets from the first zone, they are at a distance of b by 3 from their corresponding wavelets in the second zone. So, their path difference is b by 3 into sin theta. Now, b by 3 into sin theta is 1 by 3 into 3 lambda by 2. Now, 3 in the numerator denominator cancel out. So, b by 3 sin theta is equal to lambda by 2. So, if that happens, they will completely cancel out. So, the blue zone and the red zone, the contribution from these two zones will completely cancel out. Whereas the yellow zone, the bottom portion, that zone will remain uncancelled. So, that will contribute to brightness. Now, since most part of the slit is cancelling out, so therefore there will be minimum brightness. No, it will not be as bright as for the full slit. So the light from this leftover third part of the slit, so 1/3 of the slit, they will produce bright fringes. Since only 1/3 of the slit light is contributing to the screen, the intensity is much lower than the central maximum. Next. Now let us generalize this. The logic of remanence will extend to n number of zones. A secondary maximum will occur whenever the slit can be divided into an odd number of zones, 3, 5, 7, 9, etc., allowing all but one to cancel in pair. If there are odd numbers, that is combination of even numbers plus 1. So 1 will remain uncancelled. So from that point, we will get the bright point. So this will happen when the total path difference is an odd multiple of half wavelength. So b sin theta has to be equal to 2n plus 1 lambda by 2, where n is equal to 1, 2, 3, 4, etc. Next. So how the diffraction pattern will look. So if we draw intensity in the y-axis and b sin theta in terms of lambda on the x-axis, at the center we will have 0. On both sides lambda, then 3 lambda by 2, 2 lambda, 5 lambda by 2, etc. At 0, 3 lambda by 2, 5 lambda by 2. At every lambda by 2, every multiple of lambda by 2, we are going to get the maxima. At 0, we get the central maxima. So intensity will be maximum at 0. And at other points, at every lambda by 2 multiplication, of the distance lambda by 2, we will get a minimum. So that will be secondary maxima, tertiary maxima, etc. Minimum where we will get when b sin theta is equal to lambda by 2. So from the center, if we move to plus minus lambda, that will give us b sin theta lambda. That is a minimum. Then 2 lambda, that is another minimum. So that way we will keep on getting the minima where we will get that portion. Next. So what is the core principle of derivation that we have done here? The zone method is the key here. Single slit diffraction is understood by dividing the slit into zones that destructively or constructively interfere. Minima is equal to perfect cancellation that we know. So dark fringes occur when the slit divides into an even number of zones. That leads to a total cancellation. So b sin theta is equal to n lambda. Maxima is partial remnant or remaining something remains partially. So bright fringes occur when the slit divides into an odd number of zones. That leaves one zone uncancelled, and that uncancelled zone contributes to brightness. For this to occur, the condition is b sin theta is equal to 2n plus 1 lambda by 2. The intensity follows logic. The center maxima is the brightest because the entire slit contributes constructively. Secondary maxima are progressively dimmer as only a fraction 1 by 3 or 1 by 5, 1 by 7 of the slit contributes. Next. So that was a philosophical or pure physics based proof, no mathematics. Now let us look at a mathematical proof or analytical proof, what we say. The question here is we are given a plane wave of monochromatic light which is incident on a single slit. Slit width is B. What is the resulting light intensity at a angle theta on a distant screen? That is the question that we are going to answer. We'll use a model. So what we'll do is we'll treat this slit not as a single opening, but as a continuous distribution of infinite number of infinitesimal point sources. Then, by summing the wave contribution from every source, we can precisely calculate the total electric field and from it the observable intensity, and that we calculate later. Next. So we are going to deconstruct the geometry here. You can see the geometry. So monochromatic light plane waves are coming to a slit of width B. So on the slit starts from S is equal to 0, goes up to S is equal to B. So on the slit width is varying from 0 to B. Position is variable. The light position secondary source positions are variable between 0 to B. Diffraction is occurring at an angle theta, and the light coming out of the slit is being projected on a distant screen. So D, the distance, suppose we say capital D, then capital D is much larger than B, the slit width. Next. Now, we know the origin of interference is the path difference. The wave originating from a position S within the slit will travel a slightly longer path to point P than the wave from the very top edge at S is equal to 0. So this extra distance is called the path difference delta x, and we already have seen why delta x is equal to S sin theta. So at S is equal to 0, second ray is from a distance S. So the hypotenuse here is S and delta x is the path difference. Next. Then we have to translate the path difference to a phase difference. For that, what we do is we define a number called wave number k, which is equal to 2 pi by lambda. Then the phase difference of a wave from a position S relative to wave from S is equal to 0 is defined as phi is the phase difference, is equal to k into delta x. Now, delta x we know is s sine theta, so it is k into s sine theta. Remember, s is not the slit distance. S is a distance within the slit. From the top point of the slit, we have moved up to a distance s. Total slit width is b. So up to the bottom is b. So s will vary from 0 to b. Next. Now, this wave is contributing to form an infinitesimal source. We model electric field contribution dE. dE is infinitesimal electric field from a tiny segment ds as a cosine wave. So its phase is shifted by an amount ks sine theta that we have just calculated. So dE is equal to E0 by B ds into cos omega t minus ks sine theta. So this part E0 by B ds is the amplitude part. Why it is E0 by ds? Total length is B. Total length of the slit is B. E0 is the amplitude of the electric field. It is distributed over B. So over unit length, the amplitude will be E0 by B. For a distance ds, it will be E0 by B into ds. For ds length, it will be E0 by B into ds. So that is the first part. Second part is the wave. Wave nature is can be represented as sine or cosine. We are taking here as cosine. So cosine omega t. So this part omega into t. Omega is the angular frequency, which is 2 pi a, and rt is the time. So this is the fundamental oscillation of the wave in time. So this is the time dependency of the wave. Then ks sine theta. This is the spatial phase shift. Spatial means in space. So phase shift due to space. So the phase shift or phase offset due to the path reference phi s is ks sine theta. We have seen phi s is defined as ks sine theta. So this is the starting equation that we do, that we start for a distance or for a small or tiny portion of the slit ds. Next. Now, if we have to find out the total electric field due to the slit, for tiny portion it is dE. So for the total electric field, it will be E. What will be E? It will be the combination of or summation of the contribution for all points or all tiny distances ds, that is equivalent to integration. What integration will be over a limit? What is the limit? Limit is the distance of this slit. So slit extends from 0 to b. So it is integration 0 to b. Then dE. dE is equal to E0 by b ds into cos omega t minus ks sine theta. ds we have taken to the right hand side, rightmost side. Since E0, b, k and theta, these are constant with respect to s. So we are going to rewrite this equation in this form. E0 by b is outside the integral sign. Then integration 0 to b cos omega t k sine theta, we take that as one unit because that is independent upon ds, that into s ds. Now we have to integrate this. Next. To integrate this, we use a standard integration formula. Integration of cos a minus bs ds is equal to minus 1 by b sine a minus bs. This formula we know. Now, compare this with our integral in the previous slide. Here, what we will do is we will take a is equal to omega t and capital B is equal to k cos, k sine theta. If we put those things, then the integration will be E0 by B, that remains because that was outside the integral sign. that into integration. Integration will be minus 1 by b, capital B is k sine theta. So denominator is k sine theta. Numerator will be sine of A is omega t. So that remains minus B is k sine theta. So k sine theta is that we can write as k is sine theta. Limit is from 0 to b. Next. Now substitute those limits. So it becomes E0 by B k sine theta into minus sine omega t minus kb sine theta minus of minus sine omega t minus 0 because B is equal to 0. For B is equal to 0, this will be 0, last one. And for B is equal to S is equal to 0, that will be 0. For S is equal to B, that will be the first term within the bracket. Now, if you simplify that, that gives us E0 by Bk sine theta whole into minus sine omega t minus kb sine theta plus sine omega t. Now, what we'll do is we'll rearrange it. So, what we'll do is within the bracket, we'll bring the positive term, we'll make the positive term the first term and the negative term the second term. So we get the last equation E is equal to E0 by Bk sine theta into sine omega t minus sine omega t minus Kb sine theta. Next. And then this expression that we have got is a difference of two sine functions, sine c minus sine d, which is difficult to analyze. This expression is difficult to analyze in this form. So you will use a trigonometric identity. Sin c minus sin d, we know this identity is equal to 2 sin c minus d by 2 cos c plus d by 2. So then we'll apply here. What we'll do is take c is equal to omega t and d is equal to omega t minus kb sin theta. So c minus d by 2 using these values of c and d is equal to kb sin theta by 2 and c plus d by 2 using these values of c and d is equal to omega t minus kb sin theta by 2. Next. Use them. If you use them, and then E is equal to E0 by bk sin theta into 2 sin c minus d by 2, c minus d is equal to kb sin theta by 2 that we have seen from the previous slide into cos c plus d by 2 that we have found out from the previous slide as omega t minus kb sin theta by 2. So equation for E electric field, we have got this. Next. Now let us define a parameter beta. Beta is equal to, we are defining it as kb sin theta by 2. Now because k we have defined as 2 pi by lambda, if we put that, it will be 2 pi by lambda b sin theta divided by 2. So that will give us beta is equal to pi into b sin theta by lambda. So final simplification of our equation for E will become E is equal to E0 by 2 beta into 2 sin beta into cos omega t minus beta. The factor 2 inside the bracket and outside in the denominator, they will cancel out. So that will give us the final simplified equation as next. E0 E is equal to E0 into sin beta by beta into cos omega t minus beta. Now E0 into sin beta by beta, this is the resulting amplitude. It does not have a time factor. So it is only amplitude factor. Cos omega t minus beta has a time factor. So that is the oscillating term. Now this amplitude term A, that shows that the term is not constant. It depends on the angle theta. How it depends on the angle theta? Through beta. Remember the definition of beta. Through beta, it depends on the angle theta. And it determines the brightness of the pattern because brightness or intensity is amplitude square. And the oscillatory term, it shows that the light that is coming out of the slit is still a light wave. It is oscillating in time with a new phase shift beta. Next. So now what we have got here, the resulting amplitude A is equal to E0 into sine beta by beta. Intensity, as we know, intensity of light I is proportional to A square. So A square means E0 sine beta by beta square. Then we define maximum intensity. We define I0 as the intensity at the central maximum when theta is equal to 0. So at that point, beta is equal to 0. So sine beta by beta is equal to 1. That is in the form sine 0 by 0. As you know, if you put limit sine theta by theta, theta goes to 0. In that limit, sine theta by theta is equal to 1. So that gives us the maximum, central maximum. So, and if that two is that is one, then I, which is proportional to a square, is equal to E0 square. So, I0 is proportional to E0 square. So, we can write I theta as I0 into sine beta by beta square, where beta is equal to pi b sine theta by lambda. If you plot this equation, we will get this intensity versus beta curve, which is a sine beta by beta curve. Next. Now, according to that, we will get a central maxima when theta is equal to 0. And then, because beta is equal to 0, this we are using the limit beta goes to 0, sine beta by beta is equal to 1. The intensity is maximum value or I is equal to I0. Then we get minima or dark fringes. Intensity is 0, where sine beta is equal to 0, for beta not equal to 0. Um, Beta is not equal to 0, but sine beta is equal to 0 for those points. This will occur when beta is equal to n pi, for n is equal to plus minus 1, plus minus 2, etc., but n is not equal to 0. Then secondary maxima will get approximately when sine beta is approximately plus minus 1. So beta is approximately 3 pi by 2, 5 pi by 2, etc. The intensity will drop off rapidly due to the 1 by beta square denominator. That explains why the side fringes are much dimmer than the main beam or the center maxima. So I0 by 22, I0 by 61, etc. At the center it is I0, second one will be I0 by 22, third will be I0 by 61 approximately, etc. Next. So this gives us a complete picture, full picture of how you will see the diffraction on the scale. This shows us the diffraction on the scale. I is equal to I0 sine beta by beta square. Beta is equal to pi b sine theta by lambda. What do you find here? A central maxima at theta is equal to 0. Perfectly dark minima when sine beta is equal to 0. Weaker secondary maxima between the minima. Next. Now let us try to deconstruct the central maxima. Let us focus on the central maxima. The central maxima contains the vast majority of light energy. Most of the energy is focused on the central maxima. Its width is a key characteristic of the pattern. This extends from the first minima on one side, sine b sine theta is equal to lambda, to the first minima on the other side, b sine theta is equal to minus lambda. So the total linear width W is and 2d lambda by b because of this extension. So if we get that, then we get a crucial insight that the inverse relationship, in this inverse relationship, we have got 2d lambda by b. So if we have a narrower slit, b is smaller, that will produce a wider diffraction pattern. This is a direct consequence of the wave nature of light. Next. Then the fading echoes are the secondary maxima. Let us consider them. We know first maxima is I approximately I0 by 22, second maxima I approximately I0 by 61, etc. So first maxima is approximately 4.5% of the central maxima. Second maxima is approximately 1.6% of the second maxima or central intensity. Why this happens? The smaller bright fringes on either side of the center are central secondary maxima that we have defined already. They occur where the wavelets are partially in phase. Also, there are partially in phase and partially out of phase. Out of phase cancels out, partial in phase adds up. But significant cancellation still happens because of partial out of phase. That results in much lower intensity. The intensity drops off remarkably that I have just uh, described looking at the figure. Next. Now there are two phenomena. One is interference, one is diffraction. Let us compare them. In both cases, source for interference double slit is superposition from two discrete coherent sources. In case of diffraction single slit, superposition from infinite continuous sources within one aperture. Fringe width. All bright and dark fringes have equal width in interference. The central maximum is twice as wide as the narrower secondary maxima in case of diffraction. Intensity. All bright fringes have equal intensity in interference. The central maxima is intensely bright. Secondary maxima fade rapidly. So this is a comparison of interference versus diffraction. Next. So if you unify everything, the double slit reality here, you can see in a real double slit experiment, Young's experiment, each of the two slits has a finite width. Therefore, what we actually observe is a combination of both phenomena. The interference pattern from the two slits that is contained within the diffraction pattern from each individual slit. Because we have two slits, each individual slit is resulting in diffraction, and from the two slits we are getting interference. So it is a combination of both interference and diffraction. The diffraction creates the overall intensity envelope, while the interference creates the fine-grained fringes within this envelope. So they are two sides of the same wave phenomenon coin. Next. From a simple slit, a wave signature. We are trying to summarize everything now. What we have observed, a single slit produces a complex pattern of light and dark fringes, not a simple shadow. Cause for this is the pattern arises because every point within the slit acts as a new wave source based on Huygens principle that leads to a self-interference. And the result is the geometry of path difference dictates where wavelets constructively and destructively interfere. This creates a predictable intensity pattern defined by the slit width B and the light's wavelength lambda. Diffraction is the fundamental signature of light behaving as a wave. Next. Thank you for being patient and listening to it. Hopefully, it will be useful to some of you at least.